The WE&RF Endowment for Innovation and Applied Water Quality Research, honoring Paul L. Busch, was created to celebrate the spirit of innovation that he inspired in each of us. A member of WE&RF's first elected board and its third chairman, Paul recognized the need for research and the key role WE&RF could play in fostering innovation and application of new technologies.
WE&RF has been created to help assure the American people that we're going to spend our money wisely, but they want to be sure that every dollar spent on the environment gives an environmental benefit.
Paul always was trying to teach people to do things the right way, and he was always encouraging people, especially young people, to step up and try to change this business, try to make a quantum leap in the state of the art that we have.
The $100,000 Paul L. Busch Award is a very generous and prestigious honor awarded to an engineer or scientist recognizing innovation and its practical application. This year's winner will be joining a class of highly accomplished researchers and water experts. WE&RF is proud to announce that the 2016 Paul L. Busch Award goes to Jeremy Guest.
My name is Jeremy Guest, and I'm an assistant professor in civil and environmental engineering at the University of Illinois at Urbana-Champaign. I'm interested in used water, also called sewage or wastewater, and you can think of it as anything that goes down the drain or carries contaminants away from where they're generated. My students and I develop technologies that recover nutrients and produce energy from used water. And we do this through experimentation with biotechnologies. We then build models to describe the performance of those technologies, and we layer on economic and environmental assessments to understand the relative sustainability of the technologies we're developing and how to push them forward. Nutrients, and specifically nitrogen and phosphorus, are a critical challenge for the water environment. High concentrations of nutrients can result in algal blooms and cyanobacterial blooms, and these can kill aquatic life, but also cyanobacteria can release toxins that are harmful to humans and animals. To reduce nutrient loading on our surface waters, effluent nitrogen and phosphorus permits are becoming increasingly common and increasingly strict for water resource recovery facilities. And so these facilities are investing billions of dollars to upgrade infrastructure, to have their plants be at the limit of technology for nitrogen and phosphorus removal. Even with these advanced treatment processes, we can still have forms of nitrogen and phosphorus that pass through the plant and aren't ultimately removed, but that still result in algal blooms in the receiving environment. And that's because algae have evolved over a very long period of time to get exceptionally good at taking up nitrogen and phosphorus in many forms. So we're interested in developing processes that leverage these microalgae, and we want to use them inside the treatment plant. And in addition to taking up all forms of nutrients that are a challenge for the aquatic environment, they have this added benefit of fixing carbon dioxide from the atmosphere and ultimately providing an additional source of bioenergy. So they produce this bioenergy feedstock that ultimately increases the energetic potential of wastewater by about 2 to 4 times. And so we have more energy and better effluent quality at the same time. The concept of using microalgae for wastewater treatment isn't new. We've been doing it for a really long time. But the typical treatment systems are very large ponds that have to hold on to wastewater for days to get adequate treatment. And so this approach simply doesn't work for utilities that have to serve large populations. And so our goal is to really intensify the algal treatment process, get it to a really small physical footprint so it can fit within treatment plants. Our approach is to create selective pressures. These are conditions that drive natural selection in our engineered reactors, and they result in hopefully reliable and robust performance of our algal treatment process. Essentially what you're doing is engineering the reactor and the process to create a competitive advantage for the microalgae that you want. This is exactly what we've been doing in conventional treatment systems and wastewater treatment plants, but in general that strategy is much less well developed for microalgal systems. For this work, we're doing experimentation in our lab, and we're also developing models to try and predict performance of our systems under different design conditions and also simulating different environments or locations. We're really interested in this work having an impact on industry. So we've partnered with Clear as Water, a leader in this space, to leverage what we're learning in the lab and through our modeling for their pilot scale installations. Being awarded the Paul L. Busch Award is a tremendous honor. To get to join a group of such impactful researchers is incredibly humbling. And to have our work acknowledged in this way makes me really excited for the future, both for my students and I, as we continue to develop technologies for the management of used water as a renewable resource.